Okay, sir.
Okay, so this is the final week, that is the week number 12 of our course on probability theory. And so this week was all about concluding the course with this concept of correlation and then regression. Okay, so we started with correlation. The most famous, most popular correlation coefficient is Pearson's correlation coefficient. In fact, it's so famous that at least in physics, when they say correlation without any adjective, they mean this one. Okay. And we had seen this earlier as well. It is nothing but normalized covariance normalized by these two numbers, which are the standard deviation. Okay. And now, in this context of statistics, these are the sample standard deviations. All right. And the interpretation of this is that how good they fall on a straight line when they are plotted against each other. For example, you can think of two variables as players' price in IPL bidding, for example, the auction, and the performance. And it could happen that the price is, or rather, performance is proportional to the price. But that is what they expect, even though that does not happen. So the data points would fall on a straight line. Okay. And there would be some deviation, but this would be a near perfect correlation. So your rho would be something very close to 1, for example, 0.98. Okay. And on the other hand, it could so happen that those who are bought for high price perform very badly. And so there is a negative correlation in that case. And those who are bought at very less price, they are performing much better. So in this case, the correlation would be very close to -1. And what we say, the statement that we made from this would be that they are anti-correlated, okay, or negatively correlated. In real life, though, what happens is neither of these two. These two are like extreme cases. This would happen only if they are very much related to each other in some very fundamental way. Right. Otherwise, you would see a lot of variation. So, overall, in general, with players' price, you would see that there is increment in performance. Yeah. And that means that whoever are deciding the bids or bidding, those people are smart enough that they are able to, on average, guess the performance of the player. But there is going to be the lot of variation. So you see a blob sort of a thing on your data of x versus y, but you see that there is an overall increment. In this case, your rho would not be 0, but some positive value. In this case, it could be, for example, 0.5. Okay. So that means that they are correlated, but not strongly. On the other side, they could be negatively correlated as well, with some partial correlation. So this could be, for example, 0.6, because overall the blob is along negative slope line. Okay. But there is a lot of variation as well. Okay. What it means is that given a particular value of x, the value of y is not fixed. You can have large variation. And this is related to the correlation, as we'll see in the regression part. There is another correlation also, which the course is not talking about, that is called Spearman's correlation, which I've seen people use in psychology. But that is like the normal correlation, that is this Pearson correlation, multiplied by two uniform distributions. Okay. So what it gives is that freedom of choosing the functions, which are from uniformly distributed random variables. Okay. And now comes the hypothesis testing part. This is something that we learned last week. And in this case, our hypothesis would be that there is no correlation. This is what science wants to know all the time, right? Is there correlation between this and that? Is there a correlation between, for example, Earth's rotation and the amount of rainfall it receives in a given month, for example? And there is, right? There is a particular monsoon season in India at least. So there is definitely correlation there. In some cases, there won't be any correlation. So the null hypothesis is that there is no correlation against the alternate hypothesis that correlation is not non-zero. And the statistic that would be used would be this R upon standard error in R, where R is this ratio. So the correlation calculated from the data and divided by the standard error, which is square root of 1 minus R square divided by degree of freedom, which is n minus 2. Okay. And this follows T statistic, and this information is sufficient for us to conduct the hypothesis testing. Why? Because we know that now we just need to find the critical region corresponding to T distribution for a given value of alpha. That is something that we have done again and again. So once you have the critical region, you can compare it with your observed value of T, and from that you can conclude whether null hypothesis can be rejected or not. Okay. And then there is a concept of rank correlation, in which you have two kinds of data. So let's say student 1, 2, 3. Let me show you the example, which we are going to do today anyways. Where is it? Yeah, this one. So there are 1, 2, 3, 4, 5, 6, 7, 8 subjects. And for each subject, there are 2 students who are writing the exam. In subject A, student 1 got 73, student 2 got 72. Okay, so 73 is ahead of 72, etc. for each subject that is happening. And we have to find the correlation between the marks of the students in the rank sense, so the rank correlation. And so what you do is basically assign the ranks to each mark distribution. For example, for student 1, the highest marks is 73, so that gets rank 1. Similarly, 68 is second highest, so that gets 2. Then 65 is the third highest, so that gets rank 3. Now against rank 3, student 2 has 50 marks, and that has rank 5. So there is a difference in 3 and 5. Okay, so if these two numbers were always same, were always equal, then we say that there is perfect rank correlation between them, which means that we can say that A is always harder than B is harder than F, etc. But in general, you would have a difference in the ranks. So that difference will contribute to reduction in the correlation. So you calculate the difference between the rank and then square it. So D is equal to R1 minus R2, and then calculate the D square. Once you have that, the rank correlation is simply 1 minus 6 times sum over all this D square divided by n into n square minus 1, where n is the number of entries. Okay. We can do multi-correlation also. As you know that output could depend on multiple inputs. So inputs are called independent variables. So I can change either x2 or x3 to induce a change in x1. All right. And as you can see, if I keep this constant, then the change in x2 will induce change in x1 by a factor of this number, which whatever number is sitting in front of it, which is why we use this notation, that change in 1 due to 2, keeping 3 constant. Okay. Similarly, change in 1 due to 3, keeping 2 constant. All right. So this is the model for multi-correlation, and the task is to find the A123, A2123, and A13.2. Okay. And if you plot this on 3D, let's say these are x2 and x3, then x1 is a linear function of that. So that would be a equation of plane. All right. So what we are saying is that all the values, given values, lie on the plane, which need not be the case. Okay, but we are trying to best fit the plane. So which is the plane that best fits the data? So for that we have three unknowns. So we do three manipulations. First is multiply by x2 both the sides and then take sum. So this becomes sum over x2 x1. Similarly, this is sum over x2 with this coefficient. This is x2 square ka sum, and this would be sum over x3 x2. So that is one term. Similarly, you can multiply x3 and sum it, or lastly, you can just take sum both the sides without multiplying. So now we have three equations and three unknowns, these three coefficients. So in principle, we can solve it. And yeah, so you will find some solution that would be in some sense the best fit plane for it. And the standard deviation in A123 would be given by this one, which is sum over x1 minus x1 estimated from this formula. So there would be some error. The actual x1 observed will not be equal to exactly equal to this. So whatever the difference is, square it, take sum divided by n. So this is the standard deviation. All right. And the multi-correlation is given by this formula. So square root of 1 minus this standard deviation divided by sigma 1 square. All right. And then we have relation, that this multi-correlation or partial correlation between 1 and 2, given that 3 is held fixed, is combination of R12, R13 and R23, where these are pairwise correlation. Okay. And then you can derive this formula by combining these two. Okay. For example, the task could be to predict the weight of a person given their height and age. So, and with linear regression, so what we are saying is that weight is some linear combination of height and age and plus some offset. So this is exactly same as what we did earlier. This is the x1, the dependent parameter, which is a function of two independent parameters, h and age. Okay. Sorry, independent variables. So regression in general would be of this form: yi is equal to beta naught, some constant plus constant times x1. So this is the input. And the data we will have will not follow exactly this. There would always be some error. So that we denote by epsilon I, and we assume that expectation of epsilon I is 0. So the data points that are above the straight line, which are sort of underestimated by the straight line, that underestimation is exactly compensated by overestimation by the other data points. Okay. So all in all, these errors add up to 0. That is the interpretation of this thing. All right. And if you take expectation both sides now, assuming that this has 0 expectation, you get expectation of yi is equal to beta naught plus beta 1 times expectation of x1. That is one relation that we get. What we want to find is beta naught and beta 1. Okay. So there is a definition, regression of y on x. That is called expectation, conditional expectation of y given x. Okay. So this is a function of x, as you can see. And so the RSS is a quantity. It's not what you think. It's given by this sum over yi minus c plus dxi, where c plus dxi are our predicted value if this coefficient would be c plus c and d. Okay. So, and ignore the epsilon I. So this is like an error in what we are estimating and what is the actual data point. So sum over all these errors, that would give you RSS, residual square sum. And then the question that you ask is that what is the value of C and what is that value of D, which will minimize this error. Okay, so this is in some sense least square approximation. And those A and B you calculate, and that would be our estimator for beta naught and beta. Okay, so that we denote by beta naught cap. So I can say A is equal to beta naught cap and B is beta 1 cap. Okay. So beta 1 cap would be given by Sxy by Sxx. Okay, this is very important. And beta naught is in terms of this. So y bar minus b times x bar, where b is beta 1 cap basically. So first, always we find this thing, which is the slope, and that is given by Sxy, which is covariance divided by variance in x. Okay. And this number is called regression of y on x. And in principle, you can have multiple regression. So you have multiple inputs or independent variables. And so for example, if r is equal to 2, then you have two independent variables, x1 and x2. And the assumption is that they fall in plane. And then there would be these errors, which are making them in reality stay slightly away from the plane. And then we are tweaking this plane in all random directions such that square of sum of the squares of this errors is minimized. Okay. And then we can actually show the estimation of beta 1 cap and beta naught cap. These are the estimators, right? Those are unbiased estimators, which means expectation of this thing, expectation of this will be actually equal to beta 1. Okay, and similarly, expectation of beta naught would be equal to beta naught. So whenever we are approximating or estimating beta 1 or beta naught, we are not systematically overestimating or underestimating. Okay, yeah. So expectation of beta 1 is beta 1 and expectation of beta naught cap is beta naught. Alright. And yeah, this formula is actually worth remembering. So let me rephrase that. So this is sigma xi yi minus x bar can be taken outside. Sigma yi is n times y bar. So this becomes n into x bar y bar and divided by summation xi square minus n x bar square. Okay. So as you can see, this is summation xi square. Here it is xi yi. So if I replace yi by xi, I get this term. Similarly, here if I replace y bar by x bar, I get n x bar. And this ratio is your beta 1 cap. So whenever you are given a table that is basically xi and yi, you can first calculate x bar and y bar, then calculate sum over xi yi and sum over xi square, and that is all you need. Then using this formula, you calculate beta 1 cap, and then beta naught cap is just y bar minus beta 1 cap, which we calculated, into x bar, which is also calculated. Okay. And another thing you can show is that sigma square estimator, estimation in the variance, is given by RSS by n minus 2. So we can apply regression on that as well. Okay. And one take home message, which is a theorem, is that maximum likelihood estimation and least square error, both of them give the same answer, same estimator for the beta naught and beta 1 cap, if y is following normal distribution, which is generally the case. Okay. And the reason is that the likelihood function inverse exponential of this thing, and so the log of L, if you take, and it is proportional to this thing, which is exactly your squared error. Okay. And just like we said that correlation is zero earlier, now we can make a null hypothesis that beta 1 is equal to zero. Because what beta 1 equal to zero means that you have a flat line of y versus x, which means y does not really depend on x. So again, it's just same kind of statement. So yeah, in that case, the test statistics is this beta 1 cap minus beta 1 divided by square root of sigma square by sxf, and that would follow normal distribution, standard normal distribution. But sigma square is not known, so we use another fact that RSS over sigma square that follows chi-square distribution. And then we know that normal divided by chi-square, square root of chi-square, that follows a t distribution. Alright. And as you can see, if you divide this by square root of this, we just want to get rid of this sigma, right? So that we'll be able to do that. Yeah. So finally, the test statistic is the ratio of these two, which does not involve sigma. Sigma gets cancelled. And so the final thing that remains is square root of n minus 2 sxs divided by RSS times beta 1 cap minus beta 1, and that would follow t distribution with n minus 2 degrees of freedom. And once you know that, this becomes your test statistic. Calculate the value and compare it with the critical value in the t distribution, assuming that some alpha is already given. Okay. For example, if estimated slope is 0.65, which means this is 0.65, and the standard error, which is whatever this is inverse of this, right? That is 0.26 for n is equal to 36, and alpha is given to be 0.05. And the question is beta 1 equal to 0 or not? So we calculate this quantity, which is nothing but difference in the estimated and the hypothetical value. So it is 0.65 minus 0, so 0.65 divided by standard error, which is 0.26. So this t statistic value comes out to be 2.46. Now compare it with the critical value. We know how to calculate this, and this turns out to be 2.03, which is greater than 2.0. Sorry, our value is greater than this 2.03 threshold, which means that our null hypothesis can be rejected. Okay, so if we reject null hypothesis, that means that the slope is not zero. With what confidence? 95% confidence. Okay. Now comes the regression, logistic regression. And the idea is that in many times, situation is such that output variable is not continuous, it's discrete, and often it's binary. So success or failure, on or off, anything, right? For example, your visa is approved or not, given your application. Now, it could depend on many explanatory variables. For example, your income. If your income is higher, they think that you have sufficient money to travel, so they allow you, right? Or in case of emergency, you would be able to come back. So thinking that there is higher chance that they are alive. Again, it need not be 0 and 1 definitely. So there would be some probability that it is 1 given some income. For example, if your income is less than, let's say, 5,000 a month, then the probability would be very close to 0, 0.01. Then as your income increases, let's say X is income, then your probability will also increase, and eventually it will go to 1, right? If you are Mukesh Ambani, then no one is stopping you for traveling to anywhere. Okay, so the message I'm trying to conveys that P is a function of X, where P is the probability of getting a success. So the model would be that probability of y equal to 1, given that x is some value x, this is a function of x, is some p. All right. And that would also be expected value of y because y is a Bernoulli random variable. So its expectation is p. The first model we might want to consider is that p is equal to a plus bx. So as x increases, p keeps on increasing if b is positive, which means probability will eventually reach greater than 1. In fact, it will go towards infinity, which is senseless, right? Because probability is always between 0 and 1. So to have that, we first calculate odds, which is p divided by 1 minus p, which means ratio of probability of success divided by probability of failure. So now it's ratio of two probabilities such that their sum is 1. So for example, now if p is very close to 1, then this is very close to 1, but this becomes very close to 0, but slightly positive, which means this number goes to infinity as p goes to 1 from the left. Okay. On the other hand, if p is 0, then this simply becomes 0. So these odds can traverse from 0 to infinity, which means the log of that would traverse from minus infinity to infinity. All right. And this is good news because now we can fit this to a straight line. So we say that this log it is equal to a plus bx. And that is exactly what logistic regression is. And then now you can invert this equation. So you get px is equal to 1 by 1 plus e raised to minus a plus bx. Okay. And this you can see if b is positive, then at x is equal to minus infinity, this is 0. And as x increases, it slowly increases near x is equal to 0 and then again goes to 1. Right. When x is equal to infinity, then this term becomes 0. This entire thing. Anyways, yeah. So depending on the sign of b, you get three kinds of behavior. When b is equal to 0, it does not depend on x at all, and px is constant. And more importantly, that constant will always be between 0 and 1. So we are saying that probability does not depend on x. Okay. Another thing is when b is greater than 0, then p of x would look something like this. So starting at 0, then at minus infinity, then the slope would increase and the maximum slope would be at minus a by b. All right, where this becomes 0. So the probability becomes half. And yeah, then it will become 1 eventually. And for b less than 0, we have ulta, which means as x increases, the probability decreases. All right. So example of how to calculate odds is that let's say in a survey, 234 out of 300 said yes. So we can calculate odds as ratio of success by failures. So 234 divided by the remaining no ones, which are 66. That ratio is very close to 3.5. So you can say that odds are 7 to 2. So that is the language they use. By the way, if you are interested in betting games such as poker, then you can look at poker theory. There are courses on that online, which are taught in top universities. So you can look at them and they regularly talk about odds instead of probability, because then the thinking becomes much natural. Again, what you are trying to do in those games is to maximize your expected return, right? I'm betting 100, how much will I get? So that becomes much easier to calculate if you use odds instead of probability, even though both of them are equivalent. If you know one, you can calculate the other one. Okay. Now the question is how to estimate A and B. So the first method is to get likelihood. So we do MLE basically, calculate the or write down the expression of likelihood, take logarithm both the sides, and then differentiate with respect to A and B to find the answer. The only hiccup is that we cannot do this analytically. The reason is that you have A and B here, but you also have A and B here as well with logarithms. Okay, so you end up having a transcendental equation that is not solvable exactly. Alright. There are other class of models also in which px is assumed to be of this form, phi of a plus bx. Again, phi is the cumulative probability, so you know that it has to start from minus infinity and end at plus infinity if b is positive. So, in fact, any probability distribution would work, but the most standard popular one is the standard normal distribution. Okay. Now, this becomes easier. Earlier, it was only possible to solve numerically, but if x has only two possible values, 1 or 0, then it becomes much easier. And in general, if odds ratio, that is e raised to b, okay, if it is greater than 1, that means that b is greater than 0. So the slope was positive. That means probability increases with x, our input variable. So sine of b is basically sine of p prime of x, the derivative of p. In case of continuous, in discrete case, it's just increasing. All right. And finally, we can find the confidence interval for the slope b. Slope b is important, right? It tells us how much is the change in y given change in x. So that is given by the estimator of b cap plus or minus this interval, which is z alpha by 2 times the standard error. And z alpha by 2 is the critical values drawn from standard coefficient or standard normal distribution. All right, so the test statistic would be b cap divided by standard error in b cap, and that would follow normal distribution. This is something that is done quite often. It's very popular. That's why it has a name. It's called Wald's test. All right. And yeah, that basically marks the end for our, not just this week, but the course itself, as far as the content is concerned. So now we'll look at assignments. But before that, are there any questions? Okay, if there are none, then let's do assignment questions. Most of them are pretty easy. So let's do it. So the first one is that what is the value of coefficient of determination if the correlation is 0.9? So rho is 0.9 and the coefficient of determination, this is just in semantics, it's the square of the rho. So 0.9 square is 0.81. So the answer is 0.81. Technically, this is also true. Sorry, this one must be positive, right? If it is 0.81. But yeah, this contains more precise value. Okay. Next question. Correlation coefficient between x and y is 0.5. Then the coefficient of determination between 2x and minus y. So we have to just remember one thing, that rho of, instead of x, we have scaled x with some offset, and y is actually same as rho x y, which means the coefficient, the offset does not matter. The correlation just stays the same. And A also does not matter as long as A is positive. If A is negative, then the correlated becomes anti-correlated. So it picks up a negative sign. So what I can write is that this is multiplied by the sine of A. Okay. So sine of A can be written as mod A by A, which is 1 if A is greater than 0 and minus 1 if A is less than 0 and 0 if A is equal to 0. Okay. So this is only when A is not equal to 0. Alright. A is not equal to 0. And now in our case, we have row of 2x and minus y. So I can write this as row of x and minus y. Why? Because 2 is greater than 0. So this 2 does not really matter. Well, y also does not matter, but it will pick negative sign because it is minus y. Okay. So correlation between x and minus 1 is minus of correlation between x and y, which is minus 0.5. And what is asked is the coefficient of determination. So we just need rho 2x minus y square, which is minus 0.5 square, which is 0.25. Okay. So the correct answer is 0.25. Then the third one, the slope of regression line of x on y is referred to. This is again semantics, just the definition. It's not correlation because we know that slope could be anything, whereas correlation is just between minus 1 to 1. So it has to be regression coefficient, and it follows the same convention that if regression is of x on y, then it is also regression coefficient of x on y. Okay. Okay, now some calculation. The data is given for sales and advertisement of a company. So sales data is given. In fact, they have given mean. So mean sale is 40 crores and advertisement was 6 crores. Okay. And with standard deviation 10 crore and 1.5 crore. And we have to calculate, the correlation coefficient is already given 0.9. We have to find this sales for proposed advertisement expenditure for rupees 9 crore. So now, so what it is asking is that if x is equal to 9, y is equal to kitna. Okay, so for that we need this regression, which will be beta naught plus beta 1 x. And as you know, probably beta 1 is given by, and there is another formula actually, which we can directly use, is that y minus y bar is something x minus x bar, right? This is also an equation of straight line, and this is given by rho times sigma x by y or y by x. Yeah, x by y. All right. So y minus y bar is, this is our y, this is x. So y bar is 6. Sorry, I wrote the opposite way. X minus x bar would be that thing. X minus x bar is equal to rho sigma x sigma y, y minus y bar. So interpretation of x is correct. X is sales. So x minus 40 is equal to correlation, which is 0.9 times the ratio of standard deviation. Sigma x is 10 and this is 1.5, and y is equal to, sorry, y bar, the mean of y, that is given by 6. Okay. Now it's just this thing x is equal to 40 plus 0.9 into 10 by 1.5 into minus 6 plus 0.9 into 10 by 1.5 y. Okay. And now we are given y equal to 9. We have to find x. So when you do that, x becomes 58. Okay, I'm skipping this mathematical steps. It's just algebra. I mean, just numerical addition. So yeah, 58 crore. This would be the answer. Okay. Now the next data is given in which we have to find correlation coefficient between advertisement and sales using Pearson's coefficient. So these are the XI data, and these are YI data. All right. So we know that correlation is given by sum over xi yi minus n x bar y bar divided by sum over xi square minus n x bar square. All right. So for that we need sum over x square, sum over y square, and sum over xy. So that is what we calculate. Where small x is capital X minus x bar. Okay. So yeah, we always make a vertical table here. So for x, we see that sum over x is 140, which means x bar is 140 divided by 10. So 40. Okay. Similarly, y bar is 580 divided by 10. So 58. Sum over x square, that is 22. Okay. So now correlation coefficient is again, what was it? Sum over x square minus n x bar y bar. Just forgot. Sorry, this was sum over xy, right? And sum over x square minus n x bar square. So sum over xy is this thing, 70, and minus n times x bar y bar. That turns out to be n is what, 10 into x bar is 14 and y bar is 58 divided by sum over x bar, that is 22, and minus n into x bar square. X bar square is 14 ka square, so 196. So this you calculate and it turns out to be 0.7866. Okay, so that is the answer. There are no options for some reason. Yeah, so this is the answer. Okay, as you can see, once you have the knack on this, then it's just mechanical calculations. But it's important to know how to do that. Okay, now there are two time series of index numbers P for price index and S for stock of the commodity. And the mean and standard deviation of P is given, and similarly the of S are also given. We have to find correlation coefficient. Sorry, that is also given, 0.4. So we have to find the regression lines. Okay. Regression lines is always x is equal to beta naught plus beta 1 x bar. Beta naught, sorry, beta 1 y. So beta 1 would be, then what was the formula? Keep on forgetting. Yeah, we can use this one. X minus x bar is equal to rho times sigma x, sigma y, y minus y bar. Why do we use it? Because these are the exact things that are given in the question. Rho, sigma x and sigma y. Okay. So x minus x bar is 100. This is our x. This is our y is equal to rho zero point 0.4 sigma x by sigma y. So 8 by 4 and y minus 103. Okay. So we get x is equal to 0.8 y, right? This 8, 4 to the 8, so 0.8 times y and minus 103 times zero point 0.4 plus 100. That will give you plus 17.6. Okay. So this is the answer. Where is it? Yeah, third one. Okay. Now the seventh one. Again, two time series are given. Is it the same question? Yeah, it's slightly different. Instead of 8, you have 6. But we have to find the regression coefficient of S on P. Now, for regression coefficient of S on P is nothing but this number, right? 0.8 in the previous case. But now the standard deviation is different. So basically, beta 1 is rho times sigma x by sigma y. So 0.4, sorry, the rho is also different, into 6 by 4. This becomes 6 into 0.1. So 0.6. Sorry, did I do mistake? Of S on P. Okay, so this is ulta. So I have to, yeah, I should be careful here. This should be sigma S by P. S on P means S on P, literally. S on the top, P on the bottom. So now S is, sigma S is 4. This is 6. So this becomes 1.6 divided by 6. And yeah, 16 divided by 60, which is 4 divided by 15. So the correct answer is this one. Alright. Always remember that what is being asked. Because if y is equal to mx plus c, then the slope is m. But if I'm plotting x on y, then x would become 1 over m y minus c, right? So 1 by m by minus c by m. So now the slope becomes 1 by m. So exactly same thing here. Okay. Next question. We have to find Spears's coefficient of correlation between the marks of two students in different subjects. So this is about rank, right? And this is what I showed earlier also. So the idea is that you make vertical columns, and for each student you give ranks. So for student 1, subject A is the highest rank, so 1. Then B has second highest, 2. Third highest is 65, so 3 here, etc. Okay, so for every subject you have rank D, A, D, B, D, D, etc. Similarly, you do the same thing for student 2. So once again, the highest one is 74. Convince yourself. So that would give rank 1. And rank 2 is 72. And the next one is 69. Oh, so that is rank equal to 3, etc. And now we see that there is mismatch in the ranks. If there was no mismatch, then the correlation would be 100% or 1. But there is this mismatch. So we calculate this mismatch or the difference. In this case, it is -1, -4, 3, etc. Okay. And if we add them up, then we'll get 0, right? So we do not directly add them up. First, we do square and then add them up. It's just like how we calculate the variance. So sum over d square turns out to be 40. All right. So sum of the square of difference in the rank. And then the formula is r is equal to 1 minus 6 times summation of d square divided by n into n minus 1. Or was it n square? Yeah, n square. So 1 minus 6 times 40 divided by n is how many subjects? So 8 into 63. Once again, we can calculate this. Yeah. And this turns out to be slightly more than 50%. In fact, it is 11 by 21. Okay. Yeah, it is there in the option. So 11 by 21, that is the Spearman's coefficient. Okay. And as you can see, that is slightly more than 0.5, which means they are weakly correlated, but not so strong. That means that A is, for example, on average, a easy subject, because both of them are getting high ranks, 1 and 2. Okay. Similarly, this is the toughest subject, H. I wonder what it is, maybe humanities. But yeah. So as you can see that there is correlation between the marks of student 1, or rather the ranks of student 1 and 2. So that gives you this correlation of about 50%. Okay. Again, use the method of least squares to fit a straight line given this data. Correct. So it's the same thing that you do. You first calculate beta 1 cap, which is sxy divided by sxx. And you can use any of the method. I like this sum over x square minus what was that? Sorry, sum over xy and minus n x bar y bar divided by sum over x square minus n x bar square. Okay, so this would turn out to be 2.0266 plus. Then beta naught is very easy because you can take average here. It is simply y bar minus beta 1 x bar. Y bar and x bar are very readily calculable here. So value of beta naught that you will get is minus 3.2011. Yeah, it's done here, sum of the calculations. So the answer is minus 3.2011 plus 2.026. So the first one. All right. Again, the same thing, x and y are given, and we have to find the regression line. So beta naught and beta 1. So once again, same method. But since this is the final question and final question of the course, in fact, so let's do it properly. Okay, so the beta 1 cap is equal to sum over xy minus nx bar y bar divided by sum over x square minus n x bar square. Alright, so first we need x bar and y bar. X bar is 14 divided by number of entries 4. So 7 by 2, 3.5. Y bar is sum over y 51 divided by 4, whatever it is. Okay. So now this becomes sum over xy, which is 188 minus n, which is 4, into x bar 7 by 2, and into y bar, which is 51 by 4. And then sum over x bar, that is 54, and minus 4 times x bar square. X bar square is 7 by 2 ka square. So that is 49 by 4. Okay, then do some tiki-taka. 4, 4 gets cancelled. Here also 4, 4 gets cancelled. So you are left with, I think, and okay, let's do it. 188 minus 51 times 7, that is 357. So this is 188 into 2. Right? So it is 1 by 2. 2 into 188 minus 357 divided by 5. 2 times 188, that is like 360 and 376. So 376 minus 357, this gives you 19. Alright, so it is 19 divided by 10, which is 1.9. Okay, I did the calculation because A, that was the last question of the course, and B, just to tell you that this can be done even without calculators. I think in the exams they do give calculators, the virtual ones. But yeah, so that marks the end of it. Any questions? Okay. If there are no questions, then I guess let's call it a day. Yeah, thank you very much, everyone who has been attending the course. I learned a lot from you guys as well. And yeah, through the course also, I learned many new things. So thank you, everyone.
Thank you for your kind explanations for all the times and given detailed explanations and how to solve the questions you are explaining neatly. Thank you for your kind of.
Thank you, sir. That means a lot to me. Okay, yeah. So thank you, everyone. And just last note: if you have any questions for exams or any time, I'm always available. Just shoot an email to me. Okay. Okay, so that's me signing off. All of you have a great life. Thank you very much. We hope to see you sometimes.
Thank you.
Bye, everyone.